Hello there, this is Ms. Page. In this lesson, we are going to talk about how to solve exponential equations that have a base of e using our logarithm. Specifically, in a base e equation, we do use the natural logarithm, since the natural logarithm is our base e logarithm, and it will help to solve more easily and with an expression that is in a simplest form that makes it just a nicer, simpler way to write things. So we're going to start off with something that we have already talked about, and that is the value of the natural logarithm of e. And here we're going to look at finding that value without using a calculator. So one of the things that we have learned about in our properties of logarithms is, or just actually about logarithms, is that logarithms, remember, represent an exponent value. So we know that the natural logarithm of e is equal to some exponent value, let's call it y. And then any logarithmic form we can change into its exponential form. Now here we do have to recognize that ln, of course, means log base e. So what we have here is log base e of e equals y. That would make the exponential form e to the power of y equals the argument of e. And then our exponential property of equality says, well, now that the bases are both e's, then we can conclude that the y exponent must be equal to this exponent over here, which is a 1. And that then tells us, since y is equivalent to the natural logarithm of e, that the natural logarithm of e must be equal to 1. That's one way of evaluating it without a calculator. This statement right here, that the natural logarithm of e is equal to the whole number of 1, is something that will come up in our problem solving. So if we end up, or when we end up with this statement or this expression of the natural logarithm of e, we will substitute it with the value of 1 to simplify our solutions. So what we will do is, and this is assuming that we have this form of a base e equation, and this is our power equals a power form. So one of our powers will be e to the power with our exponent involving our variable, here shown as x. And then c is our second power. Maybe like it could be a number 2, it could be a number 5, it could be something else, but most of the time it'll just be a number. And so once we have that form, that structure of a power equals a power, remember we can take the logarithm of both sides, and we can take the logarithm or use the logarithm of any base that we want to. But because the base of the power that involves our exponent is e, what we would like to do is use our natural logarithm. And so you got to make sure that is of both sides. That's a common mistake, but this is an algebraic procedure like adding 5 to both sides. And so it must be for both sides. Once we have those logarithms in place, then we can use the power property of logarithms to again undo the exponent. And so now we'll have our natural logarithm, which is represented here by log base b of our power, and we can pull our exponent to the front as a multiplying factor, changing its form to this here. And again, if remember that exponent involves any addition or subtraction, it will need to be enclosed in parentheses. From here we can use our algebra skills and our undoing, our reverse order of operations to undo things to solve the equation that we now have. And then we can get it to the point to where we're done and simplify, get it into that exact solution, which I believe we're doing exact and approximate here in this lesson again. So we will be using our calculators to help with our approximate values. And then here's another way we learned about properties of logarithms, that when the base and the argument are the same, that means that the exponent value has to be 1. So in a natural logarithm, which has a base of e, if the argument is also e, then it will have to be equal to 1. And we'll use that as part of the process. Okay, here we go. So we will solve each of these equations. using our procedure. Notice it says we want to give the exact solution, which means there's no calculator required. And we'll also give the approximate solution to 3 decimal places, for which we will use a calculator. So here we have the structure of a power equals a power. So we don't have to do anything for that. That means that we can begin the solving process by taking the natural logarithm of both sides. Oh, wait, actually, now that I'm looking at it, we don't have that power equals a power. Do you notice what I missed in my analysis of my equation? So my power with my exponent is 4x. The base of that exponent is e, but I've got this 5 here. That 5 is not part of the power. So actually, to create my power equals a power structure, I need to undo that times 5 first. So I almost fell into a little trap that I sometimes see people fall into who don't recognize the difference, the structure here. So that 5 is not part of our power on that side. So now we have 2 equals e to the 4x power. Now I have power equals a power structure, where I have my base of 2 with an exponent of 1, and I have my base of e with an exponent of 4x. So now I can take the natural logarithm of both sides. So I have the natural logarithm of 2 will equal the natural logarithm of e to the 4x power. And now I can undo my exponent using that power property of logarithms, which says I can rewrite this by pulling that exponent to the front as a multiplying factor. And I don't need parentheses here because there's no addition or subtraction in that exponent. And that equals the natural logarithm of 2. Now here's where we're going to use the property of logarithms, that the natural logarithm of e is actually equal to 1. So if this is equal to 1, then what we have over here is really just 4x times 1. So this is going to simplify to the natural logarithm of 2 equals 4x. And so I continue my solving. Now I have to undo the multiplication, dividing both sides by 4. And again, you have to realize that you are not dividing 2 by 4. 2 is the argument of the logarithm. You are dividing the logarithm value by 4. And so your x is either the natural logarithm of 2 divided by 4, or some people prefer to write that as 1/4 times the natural logarithm of 2. Either way is fine for these problems because it's a solution and not a function situation. Then, so these would be forms of our exact solution. So now we're going to use our calculator to approximate this value. And so remember, we've learned that we need parentheses around arguments, but that's pretty much the only parentheses that we would need to make sure that our math turns out correctly. So let's use our calculators. So here we're getting 0.1732, and that's to 4 decimal places. So remember, we're rounding to the third, which is where the 3 is. So the 2 tells us the 3 will stay a 3. So this is x is going to be about 0.173 to 3 decimal places. And this is what we consider our approximate solution. All right. Let's take a look at this one. So again, the basic procedure is the same, but what it's helpful to see multiple examples for is to make sure that we recognize the structure correctly, that we begin the problem to create that power equals a power structure correctly, and then we go through and make sure that we're able to use our calculator correctly and all that kind of good stuff. So here in the first step, I don't have this, my power equals a power structure, so I need to create that first. And I'm going to use my undoing algebra, which is in the reverse order of operations, to create that. So I have to undo this subtraction first, adding 8 to both sides. So I have negative 3 times e to the power of x plus 2, and this is equal to negative 9. Watch your signs. then I have to undo this multiplication, because again, my exponent of x plus 2 has a base of e. The negative 3 is not part of that, so I have to undo that. So now I have e to the power of x plus 2 equals positive 3. Now I have my power equals a power structure, where one of my powers has a base of e with an exponent of x plus 2, and the other has a base of 3 with an exponent of 1. So now I can move to the second step, which is to take the natural logarithm of both sides. Here I want to use only the natural logarithm because my power with my exponent that includes the variable has a base of e. So I have the natural logarithm of e to the x plus 2 power equals the natural logarithm of 3. Make sure you do that both sides. That's a common mistake in these problems, is that students only do the natural logarithm of the e side and not the other side. That doesn't balance your equation with your algebra procedure. So now we're going to use our power property of logarithms, which allows us to undo this exponent and move this to the front. This time our exponent does involve addition, so it should be in parentheses, x plus 2. And that's now times the natural logarithm of e, which equals the natural logarithm of 3. Now, in our previous problems, when we were using our natural logarithms, we had to distribute our logarithm to the quantities in parentheses. But here, because of the special relationship that we have, we get to simplify instead. Because the natural logarithm of e is equal to the value of 1. It represents the exponent of 1. And anything times 1 is itself, so we have 1 times x plus 2, which just becomes x plus 2. So this is another reason why we like to use the natural logarithm. It simplifies our algebra here. Now, the next thing I need to do is undo my addition and subtract 2. It's a good idea here to put your argument in parentheses so that you don't mistakenly think that you are going to be subtracting 2 from 3, because you're not. 3 is the argument of the logarithm. You are subtracting the 2 from the logarithm. So now you have x equals the natural logarithm of 3 followed by minus 2. And this will be our exact solution. So when we go to do the approximate solution, we need to make sure that we put parentheses around that argument, assuming that our calculator works in the left to right format. If you work backwards, then you probably don't need, if your calculator works backwards and you put the argument in first, then it's unlikely that you need parentheses. You can just do 3, natural logarithm, then minus 2, hit equals, and it should work. But for those of us who have the calculators that work left to right, the parentheses are required. So let's use our calculators. So I have my natural logarithm of 3. I want to close my parenthesis and then do my minus 2. So here I get negative 0.9013. So our 3 tells us the 1 will stay a 1. So our approximate solution is negative 0.901 to 3 decimal places. Now remember, number sense is important here because we sometimes we're getting closer to the situation in which we're going to learn about some situations in which we have invalid number sense, and so we don't get solutions. It's like an extraneous situation. But here in this situation, x is part of our exponent, and exponents can be any real number. So negative solutions are fine in this case. And then that finishes up this problem. So now we're going to look at a different type of equation that involves powers of e. All right, and they'll have a binomial or trinomial structure. We will have our variable in multiple positions. And so this cannot be done the same way that we've done the first couple of examples. It actually has to be treated like a polynomial. And so we'll use our factoring skills to help us to solve these types of equations. So you have to see this as a trinomial structure because we have three terms. You do want it to be in standard form, which it is. Standard form would be decreasing powers of the exponent and equal to 0. Then what you're going to want to do is you're going to factor this trinomial into two binomials. And so here's what you're looking at. So this has what we call a quadratic structure, where the middle exponent times 2 equals the first exponent. And when we have a quadratic structure, then we can factor by using the powers of the middle as the factors of the first. Another way of looking at it is understanding that e to the 2x would be equal to e to the x times e to the x, because our exponent property says that if we're going to multiply these powers together, we would add exponents, and x plus x is 2x. So either way we look at it, our two binomial factors will both have to start with e to the x. All right, so now we need two factors of 6, and we need to have a minus 5 in the middle, which means we'll need two negative factors. We can either use -1 and -6, or -2 and -3. So here it's the -2 and the -3 that are going to also give us that -5. Always check your factoring before moving on, because if your factors are wrong, then it doesn't matter whether you follow the procedure correctly or not, your solutions will not be correct. So now we have a product of two factors equals 0. So remember, anytime in our math, in our algebra, when we create a product of factors equals 0, the next step will be to use our zero product property, which says that if the product of factors equals 0, then either the first factor equals 0 or the second factor equals 0. So these now have actually become similar to the equations we have previously solved. So it's like we have a more complex equation to start with. We recognize its structure is trinomial. We use those types of strategies to factor. And now we can create the power equals a power structure, take the natural logarithm, and go from there. So like this now becomes e to the x equals 2. Now I have a power equals a power structure. So now I can take my natural logarithm of both sides. I can undo my exponent here using the power property of logarithms. And instead of having to divide by and undo the multiplication here and divide by a logarithm, because I have the natural logarithm of e, I simplify it to 1, and x times 1 gives me x. So one solution is the natural logarithm of 2. Over here, I'm looking at similar process. So I add 3 to both sides. Now I have a power equals a power structure, so I can take the natural logarithm of both sides. Now I can use my power property to undo my exponent. And again, instead of having to undo the multiplication with division, I have a natural logarithm of e, which I should know simplifies to 1, giving me x equals natural logarithm of 3 as a second solution. So like other types of trinomials, x squared trinomials, polynomial trinomials, has two solutions. Here we also end up with two solutions. But I'm going to kind of pre-teach. That doesn't always happen, and we'll see why in a minute. So our exact solutions are the natural logarithm of 2 and the natural logarithm of 3. Then we're going to approximate each of those using our calculator. So our natural logarithm of 2 is about 0.693 to 3 places. And our natural logarithm of 3 is about 1.099 to 3 decimal places. So these would be our approximate solutions. All right, let's take a look at this one. So this has the same type of structure, but stay with me here because we're going to talk about in this one some situations that we need to be on the lookout for as we get towards the end of the problem. Another difference here too is that our coefficient of the first term is not 1. So e to the 2x, we'll use factors of e to the x and e to the x, but we also have to consider the factors of 2, of course. So we're looking at this being 2 e to the x times 1 e to the x, so that we can factor this correctly. So this is going to give us, for our two binomials, 2 e to the x and e to the x. And then we need our two factors of -5, of which we're pretty much fixed with either a 1 and a -5 or a -1 and a 5. So we're going to have to do some looking here. So I think we're going to put our 5 here and our 1 here. I want a +3 in the middle, so I think plus and minus. That'll give me a +5 e to the x minus 2 e to the x, which is +3 e to the x. And 5 times -1 is my -5. So that looks good. I can use my zero product property now. So I have 2 e to the x plus 5 equals 0. Or my e to the x minus 1 equals 0. Now over here in the first one I have, be aware, of course, you've got order of operations, reverse order of operations rather, to follow here. So undo the addition first. And then you have to recognize, so this is 2 times e to the x, and again, the power is e to the x. So you have to undo the multiplication, dividing both sides by 2. So we now have a power equals a power structure, where one power is e with an exponent of x, and the other is -5/2 with an exponent of 1. Now we can take the natural logarithm of both sides. We can undo our exponent using the power property of logarithms. Simplifying that gives us x equals the natural logarithm of -5/2. All right, here's where our understanding of logarithms and its parts is super important. This is actually part of our number sense as applied to logarithms. So we have learned, because logarithms are equal to exponents and the base of a logarithm is positive but not equal to 1, that means the argument, remember, has to be a positive number. And here we ended up with an argument that's a negative number. And so this tells us that this is an invalid solution. So we will not be including that in our final solution to this problem. So keep that in mind, super important. Arguments are always positive. So if you end up with an argument of 0 or a negative argument, it's invalid. You throw it out. Back up here, adding 1 to both sides gives me e to the x equals 1. Now I can take my logarithm of both sides, natural logarithm. I can undo my exponent with my power property of logarithms. And here again, instead of dividing, I should recognize that's 1. X times 1 is x. And here's another spot where Learning your properties of logarithms is important to getting this to its final simplified conclusion. So when we do our exact should be in simplest form. And when you see something like a logarithm of any base of 1, that should jump out at you. When your argument is equal to 1, your exponent has to be 0, and your logarithm represents that exponent. This is log base e of 1 equals an exponent. And so you need e to a power to equal 1. The only exponent value that creates a power equal to 1 is 0. So that tells you that your logarithm equals 0. So you simplify this to x equals 0. And that's fine. X can be 0 because x, remember, was part of the exponent. And this argument is greater than 0. And so this one was not. This one is. 1 is greater than 0. That's the only condition on an argument. So then we simplify. Natural log of 1 is 0. So this is our exact solution. And our only exact solution. And because 0 is 0, not a logarithm, there's no need for an approximate solution. So there's the approximation for 0 doesn't make any sense because 0 is 0. So there's no approximate solution needed here. Doesn't make sense. Okay? All right. Let's take a look at the next one. So we've looked at a couple of trinomial situations. We're now going to look at a couple of binomial situations. So this is our first binomial structure. And so binomials here, when we have the two powers that involve our x, will be a GCF type of factoring. So remember that e to the 2x, and here's where understanding those exponent properties is more important. E to the 2x is e to the x times e to the x, because exponent property here says to add those exponents together. X plus x gives us that 2x, which means that an e to the x is our GCF, our common factor. So our GCF is e to the x, and then that would be times in parentheses the other e to the x minus 5. And that equals 0. So now again, I've created a product of factors equals 0. So I move on to my 0 product property. So either e to the x equals 0 or e to the x minus 5 equals 0. In the first one, I've actually already got a power equals a power structure, where one power is e with an exponent of x, the other is 0 with an exponent of 1. So I can introduce my logarithms, or take the logarithm of both sides, undo with my power property of logarithms, undo that exponent, simplify. 1 times x is x, and I get x is equal to the natural logarithm of 0. Remember what we just were refreshing our memory on about arguments? Arguments have to be positive, which means greater than 0. This one's not. 0 is not greater than 0. So this one is invalid. Moving to the other one, I have to actually begin by adding 5 to both sides. Now I have a power equals a power structure. So now I can take the natural logarithm of both sides. Undoing that exponent. And simplifying gives us x equals the natural logarithm of 5. Argument greater than 0. Yep, sure is. So this will be our exact solution. Just going to rewrite it for space. So this is exact. And so now this one we do approximate because natural logarithm of 5 represents some decimal value that is going to be an exponent, approximate exponent value. And so let's use our calculators. Natural logarithm of 5. So about 1.609 to 3 places. There we go. All right. So one more, another binomial we're going to take a look at to complete our examples. All right, so here are a couple of things going on with this one. And that is, and this is why you don't just assume, don't make assumptions. Some people would assume here that e to the x is the GCF, but it's actually not. Because here we have e to the 2x and here we have e to the 4x. And so although they have an e to the x in common, it's not the greatest common factor. Also because of the 6 and the 4. It's not just an e to the x. So e to the 4x, we have to recognize, oh, that would be e to the 2x times e to the 2x. And so there's actually an e to the 2x in common with that part. And 6 and 4 have a common factor of 2. And so it's actually 2e to the 2x power that is our GCF. So 6 divided by 2 is 3. So we have 3 times e to the 2x as the first part. Always a good idea to double check your GCF factoring, especially when it's complex like this, to make sure that you're getting 6e to the 4x. And we are. 2 times 3 is 6. E to the 2x times e to the 2x, we would add the exponents. 2x plus 2x is our 4x. Minus 4 divided by 2 is 2. And e to the 2x divided by itself is 1, so we just get a minus 2 there. 2 times our minus 2, that's our negative 4. E to the 2x equals 0. So now we have a product of factors equals 0. And here we can now use our zero product property. So 2e to the 2x equals 0. Or 3e to the 2x minus 2 equals 0. Going back to the first one, we do not have a power equals a power structure. That 2 is not part of the power, so we undo the multiplication. Remember, 0 divided by any other number is still 0. And so we get e to the 2x equals 0. Take the natural logarithm of both sides. Undo that exponent. Simplify the natural logarithm of e. So this gives us 2x equals the natural logarithm of 0. And we could actually stop here. I mean, if you go ahead and divide both sides by 2, that's fine. X would be the natural logarithm of 0 divided by 2. However, remember, arguments have to be positive, greater than 0. And this one is not. So this one is going to be invalid. Moving to the second one, we have to first undo the subtraction. So we get 3e to the 2x equals 2. Then we have to recognize we have to undo this multiplication. So dividing by 3 gives us e to the 2x equals 2/3. Now we have a power equals a power structure, so we can take our natural logarithm of both sides. So the natural logarithm of e to the 2x equals the natural logarithm of 2/3. Undo our exponent. 2x times the natural logarithm of e. Simplify the natural logarithm of e. 1 times 2x is 2x. So now, dividing both sides by 2, and you can do it this way, it's fine. So now we get x equals the natural logarithm of 2/3 divided by 2. Checking our argument. Is our argument greater than 0? Yep, 2/3 is positive, so that's fine. And so you can write your exact solution either as the way I've got it here, that natural logarithm of 2/3 divided by 2, or if you prefer, some people like to do 1/2 times the natural logarithm of 2/3. Either way is fine. for this because it's not a function. It's just a solution to an equation. So this is our exact solution. So now approximating that, and you can do it either way, 1/2 or 0.5 times the natural logarithm, or putting that argument into parentheses before you divide by 2. Close that argument. So our approximate solution will be, easiest way to do the 2/3 is just 2 divided by 3. So to 3 decimal places here we get negative 0.203. And there is our approximate solution. All right, so that does go through all of the examples for this lesson. Gives you a variety for a resource, and you should now be able to start your assignment. Have a wonderful, wonderful day. Bye-bye.